Okay, so what we're going to do is we're basically going to review from the beginning of the semester till now. Well, actually, the beginning of the semester through statics of particles. And then we'll see where we are, and then we can do some review for moments if we have time. I thought let's start out with something fun. Again, pulleys, I really like pulleys. So I wanted to make sure that everybody's really comfortable with pulleys. So I'm on page 51, and it's number 267. 2.67, so it's number 67 in chapter 2. And it is the problem actually that you saw on the pulley quiz. So I just want to go over this to make sure everybody's comfortable. With these pulley problems, I'm going to zoom in now. With these pulley problems, I always start at where T is. Okay, everybody sees I always start where T is. And I follow the cable around. You know now that if a cable is continuous, it continues to have the same tension. So here is T. I go around here, and this is going to be T on this side. And in the end, I have a weight going down, and I have two T's. So where are we? Maria? Yeah. Okay. So if I wanted to figure out what the relationship is between T and W, what point should I use if I wanted to actually draw the free body diagram?
The point in the middle of the pulley.
Okay, so I'm actually going to draw the pulley itself. And I'm going to focus on a lot of different things that you guys have been asking me. I'm not going to just draw the point of the pulley. And the reason why is because one tension goes up on one side and one tension goes up on the other side. And then we have the weight in the middle. So the reason I'm drawing the pulley is because all the forces are not at the same point. On the quiz that you had 2 weeks ago, some of you drew a free body diagram of all the forces on the same point. But in this case, when forces are not on the same point, you have to draw a free body diagram of a body. So this is like a rigid, I spelled it wrong, rigid body free body diagram. And the reason why is because when we have a free body diagram of just a point where all the forces are coming off the point. So I'm looking at Matthew. When all the forces come off the same point, what are those forces called? Do you remember? Okay, Myra?
Is it concurrent forces?
Correct, correct. When all the forces come off the same point, they're called concurrent forces. Hang on a second. They're concurrent forces. And Myra, concurrent forces could only make what kind of motion for this body?
Linear motion?
Linear motion. It could either pull it or push it. But when we have forces on a body that are not all in the same point, Miles, what kind of motion can I create here?
What was the question again? Sorry.
When the forces aren't all acting on the same point, what kind of motion can they create on here besides linear motion?
Rotational.
They could create rotational motion. All right, so this was something off a quiz where some people had questions. So if all the forces act on one point, well then yes, you could draw a free body diagram of one point, and it's basically a statics of particles. But if forces are coming off different points on the body, you have to draw the whole body. Everybody good? Okay. So in this problem, I drew the pulley. We're back to you, Maria. I have a T going up and a T going up here and a W going down. So what's the relationship between W and T?
2W equals T.
Say it again.
Or 2T equals W, sorry.
No, that's okay. 2T equals W, so that means W equals 1/2 T, or T over 2. Okay? All right. Peter. Peter?
Yes.
Hey, Peter. Okay, so could you do B then? Again, start with detention and tell me what all the forces are.
Joanne, did you mean T equals W divided by 2? I was gonna say the same thing on that algebra there.
This one.
Yeah, thank you. Sorry, I guess, okay, I won't give an 8 o'clock excuse. Okay, thank you. All right, Peter, are you here? Yeah, Peter.
Yes,
So if this is T, what's this?
that is also T. on the
Correct,
other
this
side.
is also T, and then I go around, and this is
Also T.
also T. So again, if I were to draw a free body diagram of the relationship between W and T, what would I draw my free body diagram of?
Of the lower pulley.
The pulley here, this lower pulley, correct. And it would look exactly like this, right?
Yes.
We have 2 T's going up and we have a W down. So the relationship between T and W are exactly the same in the first 2. Everybody good? Okay, Tim, let's look at the next one. Again, for pulley problems, I always start with T.
Mm-hmm.
So this is T. I go around. What's this equal to?
T.
What's this equal to?
T.
T. So if I draw my free body diagram of the pulley, what do I have going up?
3T equals W.
Right. 3T equals W. Okay, Tony?
Yep.
Okay, Tony, let's do D. So here's T. It goes around here. What's this right here?
It's T.
Good. When it goes around here, what is it?
T.
And then it goes around here and it's
T.
T again. So what would this free body diagram look? I have my weight going down of a free body diagram of the pulley, weight going down, and
W is equal to a third T.
you just reversed it too.
Oh,
So,
what?
so you have weight going down, and how many T's do you have going up?
3.
3,
Right.
correct. So W is equal to 3T. So what I'm doing is I'm actually looking at, really for all of these, is I'm focusing on the pulley and I'm cutting the cables, cutting the cables, cutting the cables, cutting the cables, because I want to draw a free body diagram of the pulley. So these 2 right here have the same relationship as W and T. Okay, Victoria, let's do the third one. I start from T again. Victoria?
Yes.
Okay, so this is T. So when I come around this pulley, what's this?
T.
I come around this pulley and this is?
T.
I come around this pulley and this is?
T.
T. So when I draw the free body diagram of the pulley and I cut the cables, what's the relationship between the weight and T?
W is equal to 4T.
Correct. All right. So some things I just covered. 1, I covered pulleys. Hopefully everybody's comfortable now. 2, I covered the idea that not always can you draw just the dot for the free body diagram. When forces are not coming off the same point, you have to draw a body. So in other words, if forces are coming off the same point, you could draw a free body diagram of a point. But if forces are coming off other parts of the body, you have to draw the whole body. So if we had a piece of wood, a 2x4, and there are 4 pieces of 4 forces coming off the 2x4. Is Adam here? Amani, if I have a 2x4 piece of wood, it's 4 feet long, and I have 4 forces coming off that, what would my free body diagram look like?
You said a 4x4 piece of wood?
Yeah, 4x4 is good.
A rigid body?
Correct.
Actually, yeah.
Yeah, so you would draw a free body diagram of the piece of wood, and then you have all the forces coming off of it because the forces are coming off in different points. Okay, Angel,
Yes.
If I had a piece of wood and all forces are coming off the same point, even though the wood is 6 feet long, what would I draw a free body diagram?
You draw a particle, a little dot.
That's right. Okay. So we covered pulleys. We covered whether we're drawing a free body diagram of a point or a rigid body. And then we also talked about the idea that these are called free body diagrams for a reason. This is showing a free body. It is not, the pulley is not connected to anything anymore. I cut everything off and I only have the body and the forces. And then of course, I need to put my X and Y axis. And Bon, how was I able to determine that W is equal to T2? What did I do
Well,
in my head?
Well, it's all static, so it's not moving, but there's 2 T's going up and 1 W pointing down, so they balance out.
Okay, so
I
they
thought you said
balance
it
out.
equal to 0.
Right, say it again.
You said it equal to 0, the whole thing.
Right, right. You guys tend to use a lot of, like you set it to be equal to 0. You use it or they a lot. And I want you to be more descriptive because you're a professional. And what you want to say, Bon, is that the sum of the forces equals 0, right? Give me a
Yeah.
subject of a sentence. Don't just say it because I have no idea what you mean in it. Okay,
Right.
I know what you mean, but I want you to be clearer. Okay, so far we did pulleys, we did free body diagrams, we did free body diagrams of particles or of rigid bodies, and then we're also talking about using words for nouns and not just pronouns. Okay? Okay, so now the next step is we're going to do a problem from the textbook. And we're going to do a bunch of things for that, just like this. And what we're looking at, my computer. We are on page 72 in the textbook. So it's problem number 107 on page 72. Oh, wrong way. And what we're going to cover now is we're going to cover things that you said that we needed help with. 1, seeing things in 3D, drawing free body diagrams, components, right? And then some information that we're getting from the solution, but we're going to go in order. We're going to do a full statics of particles problem. So in a statics of particles problem, we're up to Colin. What's the first thing you do in a statics of particles problem?
You write out what's given by the problem and what you need to find.
Right, given and find. So once we read the words, then I'm going to zoom into the picture better. But right now I'm doing given and find. And obviously process is important for me. I want to see clear steps. So have a little index card of what those steps are so you're not having to remember them. Okay, so let's read Colin. Let's read the problem. It says 3 cables are connected at point A, where forces P and Q are applied as shown. Knowing that Q is equal to 0, find the value of P for which the tension in cable AD is 305. And to simplify the problem more, I'm also telling you that the tension in cable AB is 446.7 newtons. Okay, so I'm going to zoom in so you can see the words better, Colin. So 3 cables are connected at A, where force P and Q are applied as shown. Knowing Q is equal to 0, find the value of P for which the tension in the cable AD is 305 and AB is 446.7. Okay, what is given?
The tension in AD and the tension in Q.
Okay, tension in AB. And to be consistent, let's use T for tension always. use W for weight always, and use N for normal always, right? Weight, tension, normal. Okay, so TAB is 446.7 newtons. And then what else is given?
Q,
Q is given at 0. What else?
cable AD's tension.
Right, AD is 305 newtons. Okay, what else do I have to write on given?
Nothing.
How about the sketch info?
Oh.
Right.
Yeah.
Okay. Okay, now that we've seen the words, I want to zoom into the picture. So let's take a look at the picture. Okay. All right. So, oh, I didn't finish the rest. Colin, you want to finish the find? What do we need to find?
We need to find the value of P.
Yes. Okay. So I wrote my given and find. Given sketch info, the two values of the tension in Q is equal to 0. And find P is equal to unknown. Okay, or you could just say P. Okay, Daniel C, what's the next step in statics part of these statics problems?
We have to create a table of forces, magnitudes, and directions.
Great. Table, magnitude, oh, I wrote table. Forces, magnitude, direction. Okay, so Daniel, what forces are here? Daniel C, we're still on.
What problem is this again?
It is problem
Oh, thanks.
72.
Problem 72.
On, sorry, problem 107 on page 72.
Okay, thank you. Just give me a 107, almost there. Found it. Okay, I got it. So we know connected at A, forces P and Q are applied as shown. Q is equal to 0. Find the value of P is equal to P. Tension, and we know the tension of A and D. So we have tension from A to D, which we do know. We know both the direction and the magnitude for the tension of A and D.
Okay.
However, we do not know the tension between A and B and A and C because it's not given.
Actually, I gave it to you guys.
Oh.
That was an additional piece of information.
Okay, then we know those, and we also know the directions for those two tensions.
Okay, and the other, hang on, the other tension is called AC.
Yes.
So you said we don't know that, but we know the direction. Okay, what else?
Then we also have the force of Q, but that's the magnitude of Q is given, and also its direction. And P, we don't know the magnitude for P, but we do know P's direction.
Okay, so what do we determine from the, wait, hang on, Daniel H, Daniel Hall, what do we determine from this table then?
That there's 3 unknowns, so you'll need, or 2 unknowns, so you'll need 2 equations.
Right, 2 unknowns, so we need 2 equations, and it's a 3D body, so how many bodies do we need to analyze?
1.
1 body. Okay, and Daniel, what body do you want to analyze, or what point do you want to analyze?
A.
Why?
That's the center point or the origin point where all of them are connecting to.
Yeah, all the points are converging there. Okay, so given and find, I don't think people are having a problem with. Tables, I don't think people are having a problem with. You're always picking the point where all the forces are converging. So then in the end, Daniel Hall, is this a rigid body static problem, or is this a particle problem?
A rigid body.
But you just told me that all the forces are converging on point A,
Or,
right?
yeah, sorry, particle.
Particle. So we're just
Makes
drawing a
sense.
free body no problem. We're just drawing a free body diagram of point A, so it's a particle problem. Now, one thing I want to introduce now is we know that Q is 0, right? Right? So we really don't need to include it. Just skip it. Just skip it. There's no need to, why complicate the problem? Why put another arrow, put a Q, put a 0, put a vector for it? Forget it. It's 0. We're not drawing it. Okay, so now what we're doing is we're going into the free body diagram, and this is where I'm going to try to help drawing in 3D. I'm going to step away a little bit so that you also see my drawing, but I'm not sure how to do all that, how you're going to see the drawing and my drawing, but let's try it out.
How did you
Okay.
gather that Q was 0?
It's in the words.
It's in the words. Okay.
Yeah, read the words. Yeah, it's in the words. That's why words are important. Okay, so now, free body diagram. Okay, so now let's take a look at this. And many of you still are uncomfortable in drawing in 3D. So I'm going to first look at the orientation of the axis in the picture. I have X, Y, and Z. So there's the XY plane, which is a vertical plane, and there's Z coming out. So those of you who took Engineering 25, the way they drew it, did they draw it as an isometric or an oblique? Who was next? I don't think. Let's do David. I know you took it. David.
Right. This is an isometric drawing.
This is an isometric drawing. All the angles between here are off at a 30 degrees, and this 60 degree, it's off 30 degrees from the horizontal, and it's 60 degrees from each other. I'm more comfortable drawing an oblique, so I'm going to draw an oblique. All right, so I'm going to draw it big. So I'm going to draw my x-axis to the right. I'm going to kind of stick with the way they're drawing it so that I don't mess myself up. So I drew my x-axis and my y-axis on my engineering paper, and then coming out diagonal from the page, I have my z-axis. So that's my first step. Look at where their axes are. And you could draw it in an isometric if you're more comfortable. It's just, for me, I'm more comfortable with an oblique. So I draw the axes first. Then I look at the point that I'm drawing my free body diagram of, and that's point A. And I have to put it somewhere central on the page, right? Otherwise it's going to go off my page. So I'm actually going to extend my x-axis out a little bit more. And again, I'm not being skimpy on my drawing. I'm making it big so I can make it clearer. So I first want to look at where A is. So Daniel I, where is A in relationship to the axes?
It seems to be right on top of X.
Okay, so it's right on top of the X. It's above the X at 240 millimeters, right? And it's also, how far is it from the origin? Daniel, I still?
The 960?
Yes. Okay, you guys, I want to have an agreement in class that when you say an answer, regardless of whether you're sure or not, you're going to sound sure. Okay? Like nothing like, is it this, or maybe this, or it seems like this, or 960? And Daniel, I'm not just saying it about you. Everyone does it. Be sure of yourself. Who cares if you make a mistake? It doesn't matter. It doesn't matter. Just think, say what you think, and let's move on. Okay, so it's 960 over. So I'm just going to put a dot over here for A. And I'm going to write down NTS, although you don't need to write that. NTS means not drawn to scale. I'm not scaling this thing. You know, if I was doing it for design, I would scale it, and I might even draw it on AutoCAD, but, you know, I'm not going to worry about the scale. Oh, Oh, A is not on X, right? A is above X. So I'm going to go up here and I'm going to put A here. And I know that it's 240 millimeters. And I'm going to draw an extension line from point A, and I'm going to draw dimension lines. Can everybody see that, or is that too small?
It's good.
Okay. All right. And I also, now you guys are going to have no problem drawing that 240 dimension line because you know it's a Y dimension and it's parallel to Y. Well, I want to do the same thing with that 960, right? My 960 is along my x-axis, but you take a look at this. Is this correct? Let me see who's next. David L.R. David, did you take graphics yet?
Yeah, I did.
Good. Okay, that's right. I learned that yesterday. David, does it make sense that I'm drawing this line parallel to the y-axis, or should it be drawn somewhere else, some other way?
It should be parallel to the z-axis.
Excellent. It's supposed to be parallel to the z-axis. Does everybody see that? I know when I draw things off and I draw it wrong, I could see that something's wrong. Sometimes I have to look at it a little bit closer before I determine what actually is wrong, but I definitely could tell it's wrong. Okay? And if you drew it a vertical line, you would tell that it's wrong. Okay? So A is up from here. Okay, where is Edgar? Where's C? Point C.
Just let me look at the picture quickly.
Yeah.
It's on the 320 millimeters on the negative z-axis.
Yep. It's on the z-axis, so I'm going to draw the z-axis going backwards. And it's somewhere here. So I'm going to put C. And Edgar.
Yes.
Does this look right? Did I just draw that dimension? You took graphics too, right?
No.
Oh, because you're electrical.
Yes, that's right.
Okay, well, whatever. Edgar, does it look right?
No.
Tell me why.
Because you're supposed to draw it like on above the z-axis, or like parallel to the z-axis, and that
Okay.
seems like it's on the x-axis.
Okay, great. So this 320 is parallel to the x-axis. It looks like it's an x distance, but it's not an x distance, right? That 320 is a z distance. So we have to draw it this way. Okay? And again, you could use the parallel rule if you want. Okay, let's draw B now. Elizabeth.
So it's 380 millimeters from the z-axis and
on the z-axis from O, right? From the origin?
Yeah.
Okay, so let's try to make this look a little bit like it's a little bit to scale. If this is 320, let's make this out further. So this is where B is. And again, I need to draw it. What dimension? That 380 is parallel to what dimension, Elizabeth? What axis, rather?
the z-axis.
Right, Z. You know, and if you want, you could write on the bottom of drawing millimeters and then never write millimeters on the drawing at all. Just put millimeters down at the bottom and then just write the numbers. Probably would be helpful because then we don't have so much stuff here. Let's do that. Okay. All right, what else do we have to draw? B, C, we have to draw D. So now we're up to Eric.
Morning.
Okay, where is point D?
It's in the YZ plane on the negative side of Z.
Great. YZ plane, correct. So I'm going to draw Y up a little bit, and D is somewhere off at 220, right? So Eric,
Right.
that 220, what distance is that? It's parallel to which axis?
The Z.
Z axis. So I need to draw it parallel to the Z axis. And here's my point D. And then what else do we know about D?
It's 960 millimeters above the Z axis.
Right. And on what axis is that distance?
That's on Y.
Y. All right, do I have everything now? Okay, so let's draw now. So I first drew my axis and I determined whether I want to do it by an oblique or an isometric. And then I put all my points in. And now I'm drawing my free body diagram, right? So this is a free body diagram. It's not connected anywhere, right? So I'm going to take a straight edge. I'm going to take a straight edge and I'm going to draw a light line here from A to D. I'm going to draw a light line from A to C. And I'm going to draw a light line from A to B. But I'm not going to put the force going all the way to D because it's not connected. So here is my force TAD. Here's my force TAB. And here's my force TAC. So I'm still drawing the free body diagram on point A, but why do I need to have these why do you think, Gerardo, why do you think I need to have these light lines going all the way up to D, C, and B? Okay, Hyoji. Why do I have these light lines drawn all the way up to B, C, and D? I think something's cutting in or out. Is she chatting maybe? I'm going to be wrong with blinded confidence. Nice, Isaac. Okay, Yoji. Remember, say a statement, Hyoji. So how come I drew the line all the way up?
It's because tension is going towards.
Okay, good point. I always want to make sure that I'm drawing tension away, right? Tension is always drawn away from the point. Maybe it's a stupid question that I asked. Tension's always drawn away, but I'm drawing the light line so that you know that somebody who's looking at this free body diagram sees that this force actually, I need these dimensions. Okay? All right. Hyoji, what other forces do I have to draw on here? I left stuff out.
The tension of Q and F.
Right, Q and P actually, it's a P.
Oh,
and we
P.
don't really know whether, I mean, you could say yes, it's a tension because it's being pulled away, but it's just an external force. We don't really know what it is. But since we know that Q is 0, I'm not even going to draw it. And then in what direction is P going, Hyoji?
Towards X.
Right, in the positive. So here's my
Positive.
P. Okay, so in the end, I have my P here. I have my tension AD here. I have my tension AC. Oh, I really messed that one up. AC and my tension AB. And do I know any of these values? Isaac.
Which values I was taking?
Yeah, which values do we know?
We know TAD, TAB,
Right.
and Q.
Right, but we're not going to draw Q because it's 0.
Yeah.
So TAD is 305 newtons. And I always write the value on here. Otherwise, if I see a free body diagram that has a T in it, I think I don't know it. So I'm going to put the value. And TAB is 446.7 newtons. So I'm going to put that one too. So the only thing I don't know is P and TAC. And I'm going to start getting in practice of circling the unknowns I don't know. So I circled P, I circled TAB. Okay, any questions on free body diagrams?
Is circling the unknowns required or just good
No,
practice?
no, it's just what I do so I remember what I need to find. In fact, what do we need to find? Isaac, what do they want us to find in this problem?
We want to find, will you scroll back up?
Yeah.
I'm taking overall procedure notes. I'm not writing down this problem. We want the and no, P.
Right. The problem is only asking us for P, right? The problem is only asking us for P. We do have 2 unknowns in the problem, so it's quite likely we're going to need to find this TAC, but we could look at it. Maybe we could find it without finding it. Okay? So I circled P only because that's the only one I need to really find. Okay, now we're up to Jack. Oh, any other questions on the free body diagram? So does this diagram look different? Does my free body diagram look different than the diagram given? Do I have any cables drawn? No. Do I show the connection of the cable at D and B and C? No. That's all I'm drawing is forces. The other difference is that they drew it isometric and I drew it oblique. And it doesn't matter which way you draw it. Okay, so now, Jack, did I already call you? Jack?
Yeah.
Okay, so what's the next step? After we draw the free body diagram?
I would start solving the problem. Like,
Oh, what do you mean?
Separate the forces into components, maybe.
Excellent, that's what I want to hear. We're finding components first. And what are we doing with those components? Jack? After we find the components, what are we going to do?
Use them kind of like as a system of equations and then solve for variables.
Yes, but before we move on to the system of equations, what are we going to do with the components?
Sum them up as sum of forces.
Let's pass, okay?
All right, pass.
Okay, Jason, Lavoy. After we get the components, what do we do?
Yeah, I was thinking about that. Let me think.
I'm glad you were thinking about that. Come on, you guys.
I know, right?
Pass, Jason. Okay,
All right.
Jason Lee.
Can you repeat the question again?
Yeah. After I solve for the components, what do I do before I do systems of equations, the equilibrium equations?
Set that up as resultant.
No.
Oh, checks.
Oh my God. Checks. That could be my favorite word in this class, you guys. Checks.
Balances.
Why the hell are we finding components instead of just shoving them in the equilibrium equations? Jordan, why are we finding components first before we put them in the equilibrium equations?
So that we can check everything?
So we can check everything. So we know halfway through the problem whether we made a mistake or not. You guys have caught my mistakes already on my homework. Okay? All right. Components. So let's look at this now. This is more practice in 3D. More practice in 3D. So let's pick TAD. That's one given. And you know how to do this, guys. We've been doing this. You've been doing this in the summer. Remember that wonderful summer homework I gave you?
Oh, yeah.
How wonderful. Okay, TAD. The magnitude is given, 305. I write the magnitude. Is this an angle or where are we? Hang on. We are on Cody. Laura, is this an angle or ratio problem, Laura?
Ratio?
How come? Did you say that with confidence?
Yeah, ratio.
Great. Okay, why ratio?
Because you're giving the distances and all that.
Right. Okay, so everyone, look over here. I'm going from A to D, going from A to D, and here's my x-axis. Oh, let me say this too. Even though I draw, or you draw a nice, neat free body diagram, the drawing given is always way nicer. So whenever I look at distances, I always look at the one that was given because it's going to be way better to read. Okay, so look at where the x-axis is. Laura, going from A to D, how much do I go on the x-axis?
960.
Oh, was that said in a question?
It's 960.
Great. And is it positive or negative?
Negative.
Right, because it's going in the negative x.
Yes.
So negative 960i. And how about in the y? Is it positive or negative?
Positive.
And how much is it in the y?
960.
960, get up. No questions. And how about z?
It's 0.
Try again. I'm going from A. A is above the x-axis, and D is over.
It's going in the negative z, 220.
Great. Okay, and then underneath I put this 960 squared plus.
I don't think it's 960 in the y because it's up 240.
Going from A. Oh, great. Nice, Maria. Even looking at a nice diagram, I screw up.
I do it all the time. So
Okay. All right, so you're right. Laura, do you see that? Up from C it goes 960, but A is up in the air. So it's 960 minus 240. Nice. So it is 720. I just said that with a question mark, with a question. 720 it is. And then tell me if it's wrong. You know, it's interesting using this textbook. This textbook almost always gives us a whole number. The other textbooks I've used have not. In the real world, they're not whole numbers always. Yeah. So this turned out to be 1220. Close the parenthesis and put my units. What's units? Newtons. You guys, you're leaving units off. Craziness. Remember what I said. Now with components, you can skip the second step. Look at that, it's coming out to whole numbers. Boy, you and Johnson like to make it easy for you. Okay, here's my component. Now I do my checks. 240 squared plus 180 squared plus 55 squared equals, under the radical, 240 squared plus 180 squared plus 55 under the radical is 300. Uh-oh, I got 300.
I think you forgot to square the 200.
Oh yeah? Okay. Yeah, no, I got 305.
Yeah, because you wrote 240 on that, the second one. Oh, sorry, wrong. I meant on the 220 up above, it's not squared. I think that's what Amani meant.
Oh, here.
Yeah.
Okay, thank you. Okay, great. So I did one check. Okay, Liam, what's the other check I want to do?
The plus minus visual check.
Okay, so walk me through it. I got a negative in the X. Explain to me if that's right using the picture.
Yes, the tension AD goes in the negative X direction.
Great. What about the Y?
It goes in the positive Y direction.
And the Z?
The negative Z direction.
Great. So look back at the picture and make sure you do the check. No longer do I want to see okay checks for positive and negative if it was wrong. Okay, you got to look back at the drawing. Okay, we got to do the other two. So should I let you do the other two? I'll do them while you're doing them and we can check them all. Keep your eye on the axes. Always look back at the axis when you're trying to find the dimensions. Oh, I don't have to do that. Hello, Oscar. Okay, this is what I got for TAC.
What's the value for TAB? The
446.7.
okay.
Okay, so some of you might even feel faster than me, huh? Can you read the numbers? And then the only other one is P is equal to P, and it's in the positive I direction, newtons. How about everybody look up when you finished all the components and the checks? And then I label my pages 1 of 2 or whatever. I probably need 3 pages, so 1 of 3, 2 of 3, 3 of 3. Okay, so yeah, make sure you're looking up so I know you're done. All right, and those of you I can't see the screens of, I don't know where you are. So, I mean, whether you're done or not. No, I'm sorry, I didn't mean whether you're here or not. I meant that I don't know if you're done or not. because I can't see your eyes. I can't see your face, so. Maria, you still working? Or you got them? You finished?
I messed up, so we can.
Okay, so you determined you messed up because you did a check and it didn't work. Yeah?
No, I did my checks, but they were fine because I messed up on where the basically the dimensions or the
Okay.
directions. So
Okay.
that's the frustrating part for me is like sometimes you go through the problem and you do the checks were fine except for
Right.
the last, but I didn't even realize that I was looking at the wrong point until the end.
Yeah.
I looked at yours.
Okay, so yeah, that's true. If you get the wrong dimension in the end, it will check too. But that's all it is that you wrote down the wrong dimension, right? But your process, the whole statics thing is all correct, right? So if in the end you get the wrong answer, what could possibly happen, Maria, is in the end, and let's talk about that anyway. Well, let me go back to this. So remember, given and find first, table next, free body diagram next, and it is a free body diagram. And you need to practice drawing in 3D if you're still having issues. Next step, components and check. So what's the next step for this? So let me see where I am. I think Luis, I think I'm up to you.
Yes.
After you've found all the components and the checks, what's the next step?
To make a matrix and solve for the unknown P.
Okay, a matrix, but probably before you make the matrix, well, I guess you could make but tell me what it is that you're doing. You're not just making a matrix, you're doing
You're solving
what?
for the unknown variable P.
Yeah, you're doing solving for the equilibrium equations, right?
Correct.
Right? You're solving for the equilibrium equation, so it's 3 equations, 3 unknowns, and then you plug them into a matrix.
Well, you
So-
can do it by hand, but matrix would be faster.
Yeah, sometimes you can't do it by hand with a 3D one. It would take forever. But you guys should all know how to do it by calculator because many of you have calculators to do it. It's basically, and it's a requirement of the class that you have the good calculator to do it because you don't want to be the one who's taking 3 hours to solve a problem when with people with a calculator could do it in an hour. Right? If I had a timed exam, you would run out of time and you would never finish it. And it's not because you don't know statics, it's because you don't have the tool. So you guys need to get a calculator that does matrices. And you're going to see it. You're going to need it in circuits and you're going to need it in junior and senior year too. And if you don't have one and can't buy one, then talk to Kelly in the STEM Center because they are loaning things out. Actually, the Watsonville Center is loaning out calculators too. Okay. All right, so the next thing is systems of equations. So should we go ahead and do that? I need to find out, this is a review for you, so I need to find out, is that what we want to do? Do we want to write out the equations? Do we want to set up the matrix?
Maybe just a setup would be nice to see.
Okay, so I'm first going to do the equations. Sum of the forces in the x equal, so it's negative 240 minus 0.9231 TAC minus 404.6 plus P is equal to 0. So there is, if you do sum of the forces in the X, all the forces are in there and it works out to be that it's 0.9231 TA plus P is equal to 444.6. So this turns out to be my equation 1. So for equation, for sum of the forces in the X, I put all the X components of all the forces I found, and then I put all the variables on the left side of the equal sign and the whole numbers on the right. Sum of the forces in the Y, 180 minus 0.2308 minus 101.1 equals 0. Oh, did I screw something up here? I must have. Yeah. TAC. So sum of the forces in the x of y, y, and y. So it means 0.2308 TAC is equal to a negative 78.9. And then I'm going to do sum of the forces in the z, and then we'll speak about it. Negative 55 minus 3077.
Joanne,
Yeah.
wouldn't
I
the
make-
constant for f in the x component be 644.6?
Did I add the math wrong?
I
Yeah.
believe so, yeah.
Yep, yeah. Thank you. See, and there, even when I'm doing it neatly and organized, I still make some mistakes, right? But at least my peer, my fellow engineer, or my boss who's checking my work is going to see that I made a mistake. When you don't set it up neatly, it's hard to find the mistakes. Okay, negative 55 minus, thanks, Angel. Gotta use a calculator. 160.1 minus 55. Let's just finish the math and then and now I'm making math mistakes on purpose. Okay, where are you guys? Did you set up all three equations already?
Is that a?
I have a mistake in here.
Yeah, Joanne, I think what's throwing me off is we have too many equations. You actually don't need three.
Right. But we'll see why we're doing it. Okay, did everybody write down the three equations already? Yeah. Okay, so let's go back. I'm going to look at my free body diagram. Could everybody stop doing the calcs and look at what I'm doing? If I do, when I do sum of the forces in the x, how many unknowns am I going to, let me see who I'm up to. Mackenzie?
Yeah, I'm here.
Okay, when I do sum of the forces in the x, how many unknowns do I have in that equation?
1.
Actually, there's 2. If I do sum of the forces in the x, I have P. Could you see my free body diagram?
Yeah.
I have P and I have TAC, right? I could write it up here. Maybe it's clearer. So I have P and TAC. That's 2 unknowns in one equation. Can I find either one of those unknowns if I have 2 unknowns in one equation? Mackenzie?
No.
No. Okay. Let's look at some of the forces in the X. Marcine, some of the forces in the Y. How many unknowns do I have in that equation?
Just one.
Just one. Because which one?
TAC.
Only TAC, correct. How about if I do some of the forces in the Z? Maria, how many unknowns do I have in that equation?
Just one.
Just one also. So what would be the most efficient to solve this problem? Do you want to do some of the forces in the X first, or some of the forces in the Y, or some of the forces in the Z? Matthew. Myra.
Sorry, could you
Matthew.
repeat the question?
Would it be
Repeat the
is it most efficient to do some of the forces in the X first, or some of the forces in the Y or the Z first?
the X? Sorry,
Okay,
the X.
I'm thinking, Matthew, you probably weren't listening when I was teaching, so listen when you're in the class. Hey, Myra?
Yes.
Okay, Myra, if the sum of the forces in the X has 2 unknowns and some of the forces in the Y and the Z have 1 unknown, which equation would you rather do first?
Either Y or Z.
Y or Z. All right. So what I did where I went brain dead for a moment. I wasn't thinking. I just went ahead and started doing some of the forces in the X. I don't want to do that again in the future. It's a waste of time. Okay. So had I did some of the forces in the Y, I would have found out what TAC is. Why? Can you think of, Miles, can you think of any reason if I solve for TAC using some of the forces in the Y, can you think of a reason why I might want to do the sum of the forces in the Z if it also only has TAC in it?
Because you killed 2 birds with 1 stone, right? You get
Yes.
the TAC for both equations.
And what's my favorite word in statics? 5-letter word, not a 4-letter word.
Checks.
Yes, check. So if I did some of the forces in the Y that only has 1 unknown in it of TAC, and I calculated TAC of doing 341.8. Did somebody else get the number yet? Did anybody get the number? If we two of us did, we're probably right.
You told us to stop calculating.
Oh,
I could
okay,
finish it if
okay.
you want.
No, it's okay. Peter, did you get it? I saw you come on.
Yeah, for both EF.
You got it. Okay, great. Thank you. Okay. So what I did then is I did some of the forces in the Z because then I could check it. But let's see what I got. This is another important thing that I wanted to cover today. I got a negative tension. Tim, am I allowed to get a negative tension?
You are not in this case because that would be compression, and ropes won't take compression, these cables.
Did everybody hear that? Say that again, Tim, but louder and really with a lot of meaning.
Basically, if we have a negative tension, that means that it's under compression. And because these are cables, they cannot take compression.
So that means, what does the negative then tell me?
We did something wrong.
I screwed up on the math. So let me look back. So it was a 55 negative. It was a negative 37. It was a positive this. Ah, I see. I forgot to carry down the negative, so it's a positive. So, Tony.
Yeah.
Besides tension, we just heard from Tim that if we get a negative tension, it means we screwed up the math somewhere.
Mm-hmm.
What are 2 other forces that we've seen that we know their direction of? Definitely, and we should never get a negative.
The other two cables, TAC.
Okay,
and-
in this problem, yes, the other two cables, but besides cables, what other kinds of forces do we always know the direction of? There are two of them.
You talking about P and Q, or are you talking like
No,
the,
just in general, not this problem, in general.
I don't know, the axes?
No, forces. Hey, Tony, I'm gonna have you pass, okay?
Okay,
But I
fair.
know you know it. Okay, Amani, no, Victoria. What other force do you always know the direction of in a problem? Victoria?
I have no idea.
When you get on a scale, look at
Yeah, wait, was
Edgar's
it
fingers. Weight. You
Okay.
always know weight is down. If the weight is unknown and you get a negative weight, there's a problem. You made a mathematical mistake. Okay, Victoria, you want to think of another one? So tension, you know, is away. Weight, you know, is down. And what's the other force you know the direction of?
The normal?
Yay, normal. We always know normal is towards the body. So if we get a negative for tension, for weight, or for normal, it means we made a mathematical mistake. Amani, if we get a negative for any other kind of force, what does it mean?
That it's probably going in the other direction.
Is it probably?
No, it is.
It is. It's going in the other direction that what you drew on the free body diagram. But you leave it as a negative because you already drew it on the free body diagram, and the answer, the solution is always the free body diagram and the numbers. Okay, so let's go back. For these statics problems, given, find, table. Oh wait, no, I didn't finish. We didn't finish the problem. So we found TAC, and in the end, we substituted in the sum of the forces in the X equation, and we get a P of equal to, anybody get it?
Yeah, I got 960.16.
Okay. Peter, did you get that one too?
Yes.
Okay, great. Good. Okay, so let's just go back. Given in all statics problems, given and find, table. Number of unknowns tells you how many equations and tells you how many bodies. You choose the body to draw. If all the bodies are on one point, you draw it of a particle. If all the forces are on a complete body, you have to draw the whole body. Then you do components and checks so that you know as you're going through the problem, you're able to check your own work before you go on and finish. Then, Angel, can you tell me, I certainly did not do the systems of equations, the equilibrium equations in the most efficient way. Angel, what should I have done?
You could have put it into a matrix to solve for it.
Yes, good. I could have used the matrix, but even before that, I have to find, you have to set up the equilibrium equations for me, you guys. You have to write down, you have to write down the equilibrium equations, then you could put them in a matrix. Okay, we'll go back to Angel. Mani?
In that Y equation, the sum of forces in the Y, you forgot to carry the negative on this to the second equation.
Let's see.
Yeah, the one under it.
Oh, I actually multiplied both sides, I think, by a negative because I moved this 2308 TA to the other side. Oh no, yeah, you're right.
Mm-hmm.
Yeah, okay, so yeah. Boy.
So you got two negative tensions.
Yeah, two negatives. Thanks, Amani. Okay, so going back to, thank you. Let's go back to what Angel was saying. Regardless, you guys, we have to set up the systems of equations. You have to write down, did you hear me? You have to write the equilibrium equations. Mm-hmm. Then you could write the matrix.
Yes.
I may not have checked your homework. I mean, I have maybe not, didn't even grade the homework for this yet. You have to write the systems of equations. Sorry, you have to write the equilibrium equations. Then you could go ahead and put it in a matrix if you want. Let's put them in a matrix. So I know the first row represents equation, each of the equations. So let's see. Equation 1 is negative 0.9231 up 31 TAC, and it's 1 times P, and it's 644.6. And the next equation, well, see, you can't really do, you're not going to do it like that. This is only, it's too easy to do it like that.
It's really easy, yeah.
Right. So we knew this was coming at the table because we only had 2 unknowns.
Yeah.
So that gives you a hint that it's unusual for a 3D problem because usually you have 3, right?
Right.
Which is why you
Usually
did
it's
the matrix
3.
math.
Right.
So because it came out to 2 unknowns, it was a hint ahead of time that the algebra was going to be easy. You only need 2 equations.
Excellent. So David's going back to the table and saying, shoot, there's only 2 unknowns. You're only going to need 2 equations. But again, you could do the third equation as a check. In fact, everybody's listening? Here, you only had to find P. They didn't even ask you to find T. If you had one equation with only P in it, you could have stopped there. You only needed to find P. I think we should take a break, and then I'm going to go over this problem one more time, okay? Because it's been a long time already.
That sounds very good.
Okay, so how about come back at 9:35? You have 12 minutes. Hello. I see, Laura, you're asking about the meeting password. I think it's ENGR35. But let me look it up.
We have a password.
Well, I think if you go in through Canvas, you don't need it, but if you go in from the outside, I think. Let me just see if I could even see it.
Yeah, if you give someone the link, then you don't need the password.
Yeah, and I don't, what I'm looking at right now in Confer Zoom. So if somebody has the session ID, do they need a password? David, are you saying no?
If they type in the number, they need the password. If they click the link, they don't need the password.
Okay, let's see. Yeah, I don't know. And then also, I'm kind of a substitute. I'm not even the host, so I have no idea. Okay, we're going to get started in a minute. Okay, we're going to get started. So let's just go back through the problem. In the problem, we were given TAD, we were given this tension, we were given TAB, we were given this tension, and we also were given Q, which was 0. So we determined that there were really two unknowns in this problem, P and TAC. So in our table, we wrote down two unknowns, which meant we needed to have two equations. And because it's a 3D, we need one body, and we picked point A because all the forces converged on that. But in the given and the find, we found that the only thing they really wanted us to find was P. So we may have only needed one equation. In the end, when we went through and we did the table, we drew the free body diagram, we got the components, and we set up our equations, we found even by looking at the picture that when you did sum of the forces in the X, the P unknown and the TAC unknown would be in there. If we did sum of the forces in the Y equation or sum of the forces in the Z, we only had the TAC. So we could solve TAC by only one equation, but we did need a second equation. In the end, we had to get both unknowns. We had to solve for both unknowns to find only P. Okay. As we move on and do more complicated statics problems, as soon as we're finished with, figuring out how to solve for moments in every possible way, we're going to see more complicated problems, and we're going to be very strategic on which equation we should solve first, because we may have a bunch of unknowns. Okay. And then it just decreases the math work we have to do. So part of the solution was drawing the free body diagram. So I'm hoping that you're getting more comfortable. Just keep doing drawings. Take out the statics textbook, and every single problem, do the drawing, so that you get better at drawing in 3D. And remember that when you're looking at the picture and you're trying to find the X distance, look in the X direction to find the X distance. So the distances are always in parallel to the X, Y, or Z. And then when you go to draw the 3D drawing, the free body diagram, make sure that you're drawing these distances parallel to the X, Y, and Z, depending on what the distances are that they're giving you. Okay, and then the last thing we looked at is, well, we know the importance of the reason to find the components first before we do the equilibrium equations is so that we can do a check as we go along. And then I want to reiterate that you do have to write down the equilibrium equations for me. You have to write down the equations. Then you could solve for the unknowns any way you want, doing it math, doing the calculator systems of equations, doing matrices in the calculator, whatever you want. But you do need to set up the systems of the the equilibrium equations. Did everybody hear that? You must set up the equilibrium equations for me. And then the last thing we looked at is if we get a negative, and let's see who we're at right now. Maybe Bond, maybe we're at Bond. Bond, what are the three forces that cannot have negatives? Because we know what direction they're supposed to be in.
Well, we can't have a negative weight.
Right?
We can't have a negative normal.
Right?
I'm just trying to think of the third one right now.
The third one was the one that we just did in our problem.
Oh, P.
Not P. The tension.
Oh.
Right? We know tension's drawn away from a body along the cable. We know weight is always going down, and we know a normal is always going towards the object away from the surface. Those three we always know. Okay? Okay, so let me come back to you guys now. Okay, so those are all the topics that I wanted to review. But certainly I could review more topics. We can move on to reviewing. We still have 20 minutes left. We could, I could can't end lab and then I save some of the time that I owe you. Or I could continue, and actually this class is supposed to end at 10:05, so we actually have 25 minutes. Boy, I'd be down to 5 minutes. Or we could do
Moments?
Moments. No. Yeah, moments. Moments. I had a moment there. Okay, so you want to go into moments? You ready? Okay. So let's do a summary first, okay? Okay, I'm going to write it down. Okay, you ready? Do you mind if I write it down? Okay, so we first started out by finding moment about a point. And we did it two different ways. The first way we did it is called the right-hand rule. And the second way we did it is what I refer to as vectorially. And let's just do vectorially first. If I want to find a moment about point A, R cross F, and F goes from B to C. Everybody with me? If I want to find the moment about point A and the force goes from point B to C, Colin, what does my R vector go from and to?
It goes from the point that the moment is about to the force.
Right, to the force. And I usually do it to the tail of the force, but we learned that we could do it to any point along the force. Everybody gets this? So for me, I always do it to the tail of the force. So the first letter here, first subscript, is always the point you're finding the moment about. But you could do it to the head of the force. It doesn't matter, because remember, if I have a point B, point C, and here's my force BC, remember, it's along that line of action. I could move that force to point C if I wanted. I could move the force up here. So it doesn't matter whether, here's point A, whether my R vector goes from A to B or it goes from A to C. It doesn't matter. Because in either way, when I cross the R vector to the force with the force vector, I'm going to get a moment, I'm going to get rather a vector that's perpendicular to both of them. You got it? And if my force and my R vector, let's say this is my force vector and this is my R vector, are on the XY plane, the moment I find is either positive or negative, and it's about the Z axis. Good? Questions about solving for moments vectorially? Okay.
Scroll up.
Yeah, Jason, what?
Scroll up.
Scroll up.
Scroll up. Thanks.
Yeah. So if I have a force and my force and my R vector are both on the XY plane, my moment's going to be about the Z axis, and it may be positive or it may be negative. Okay. Okay, so now let's go to the right-hand rule. We're up to Daniel C.
Hello.
Hi. So if I'm trying to find the moment about a point, and I'm using the right-hand rule, how am I calculating the magnitude?
Isn't it, sorry, it's going to be the force that's perpendicular to our R vector.
Well, the force is always given, right?
Yeah,
so we have no control over the force. The force is given in whatever direction it is, but we have control of finding the perpendicular distance, right?
Yes.
Right. Okay. So we find the magnitude. We find the magnitude by multiplying the absolute value. I'll just put this like this. By finding the absolute value of the force times the absolute value of the perpendicular distance. And we find the direction. Daniel Hall. We find the direction which way? How do we find the direction using right-hand rule? Daniel, it looks like it's going back and forth from mute to no mute to mute to no mute. Can I hear
Hello,
you?
can you hear me now?
Yeah, I can.
Sorry, I don't know what happened. Can you
Okay.
repeat the question real quick?
So how do I find the direction of a moment using the right-hand rule?
So your fingers are pointing in the direction of the force
Okay,
with your palm facing towards the point.
right. And then if it's clockwise, it's counterclockwise, it's positive, and clockwise, it's negative.
Yeah, and that's based on like where your thumb is facing towards you or away from you.
Correct. Okay, so now, Daniel I. Let's say in our problem, we can't see what the perpendicular distance is. What do we do? Is Daniel I still here?
Find it vectorially then?
Say it louder.
Do we solve for it vectorially? Like
Solve for what? You're saying it.
the perpendicular distance.
So let's say we can't figure out the perpendicular distance. What do we do with the force? Let me right up here. If you know the perpendicular distance, this is what you do. If you don't know the perpendicular distance, what do you do to the force, Daniel? You're still muted. Should I go on?
Yeah.
David L? Oh, Daniel, okay. Yours is going back and forth to mute and not mute too, Daniel. Aye.
Oh, okay. Sorry.
Okay, so if you don't know what the perpendicular distance is, what do? You could pass, kiddo.
Yeah, sure. I'll just...
Want to pass? Dave?
Yeah.
David?
Okay, I think if the perpendicular distance is not easy, then you break the force into components,
Right.
and then you have to add up each component's moment.
Right. You break force into components, and then you do R cross F, and you would do it as the absolute value of the X component of the force times the perpendicular distance, times its perpendicular distance, plus the Y component of the force times the perpendicular distance. And I have, let me go to David LR. David LR, you here?
Yeah.
David,
Uh-huh.
if it's a two-dimensional problem, and you're finding the moment about Z, you guys, I'm kind of doing something a little bit different, or just asking it in a different way, just to get more depth. If it's a two-dimensional problem, and I'm trying to find the moment about Z, and the force is in the X, what direction is the perpendicular distance in?
Is it in the Y?
Yes. Tell me now confidently.
It's in the Y.
Great. How about here? If the moment is in the Z and the force is in the Y, what's the perpendicular distance in?
In the X direction.
Right. We hadn't talked, when we did a 2D problem, we didn't really talk about the direction that the perpendicular distance we're in. But if we're working on a 2D problem and the moment is about the Z axis and the force is in the X, you know the perpendicular distance is going to be in the Y. Because when you cross oh, I should have another double line here. When you cross R cross F, you get a vector that's perpendicular to both of them. So if one is X and you're trying to find a distance that's perpendicular to X, it's Y if you're trying to find the moment about Z. So when using the right-hand rule, if you do know the perpendicular distance, the moment about a point is equal to the force times the perpendicular distance, that's the magnitude, and then the direction is plus or minus using your right-hand rule. If you don't know the perpendicular distance, you break your force into components because the distances given are always in X and Y. So, excuse me, find the force in the X, find the force in the Y, and do it separately. But the moment, and I remember Maria asking this question once, the total moment is going to be each force times its perpendicular distance.
And this is what the table or the chart is for.
Well, I only use the chart when I do it in 3D. Right?
I'd be curious to see what it looks like in 2D. Just
well, it would just be a 2 by 2.
Mm-hmm.
Force.
Just to take a simplified case and then kind of understand that from
force. Well, it would only be a 2 column. It would be like this.
Middle row.
So this would be the force. This would be the moment about Z and whatever its units are. And this is whatever its units are. And then this would be the force in the X and the force in the Y. And then you would put force X magnitude times the perpendicular distance in the Y. And you would put plus or negative, the force in the Y times the perpendicular, I'm going to use R, perpendicular distance in the X.
And no total row?
And the total column, the moment about whatever point it is, would be equal to the sum of all this.
But, okay, but you usually put that in the last row, no?
Yeah, that's true. You could add another row. Yeah, that's a good point. You could, sure.
Just for consistency, so I have a basis of comparison.
Yeah, good. So the moment, here's the total, right?
Total is what you say. Mhm.
Total, right? And this is the total of the above. Good.
Cool.
Yeah.
So I remember what threw me off about this at first is in your equation for breaking it up into components, you have to manually insert those signs. You have to do your hand rule for each piece, right?
Yes.
Okay.
Yes. Yeah. Because when you use the right-hand rule, you got to think about this. When you're calculating the magnitude, it doesn't matter if the force is negative or positive. It doesn't matter the direction of the force. It doesn't matter what the perpendicular distance is. You're taking the magnitude of each value to find the magnitude of the moment. And then you use your right hand to determine whether it's positive or negative. Right? So look at this. We have a point A I want to find the moment about, and I have a force here. Right? Let's say it's 100 pounds. And here's my perpendicular distance. And let's just say this is X and this is Y. So the force is in the negative X, right? Let's just say pounds. And let's say 2 inches. Okay? And this is in the Y, right? So when I say the moment about point A, it's equal to the absolute value of the force. The force we know is going in the negative X, but I'm not putting in a negative. It's the absolute value. And it's the absolute value of the perpendicular distance. So moment about A is 100 times 2. Notice I didn't put in any negatives. It's equal to 200 inch pound. But now I use my right-hand rule. Put your right hand, use your fingers, go in the direction of force. Palm goes towards A. Is this a positive or negative moment? Edgar.
Positive.
Right. So it didn't matter that the force was in negative. I could put in a negative 100 if you want, you know, and a whatever you want to call this, 2 or negative 2. But it doesn't matter when you're doing the magnitude. You're only looking at the absolute value of the force and the absolute value of the distance. And then you do your right-hand rule to find out whether it's positive or negative. Sorry, I had to blow my nose. Okay. So we started out when we did moments. The first thing we did was a 2D problem, right-hand rule. The next class we did a 2D and 3D problem vectorially. The next we did is found the moment about a line vectorially. And then what we just did on yesterday, was right-hand rule in 3D. So we have about 10 minutes left. What would you like to do now? You want to do more right-hand rule in 3D? You guys get to choose.
Jen, it might be interesting to illustrate some of the things we were discussing in office hours yesterday in regards to using the right-hand rule and in 3D with palm to the point versus palm to the axis.
Ah, okay. Okay, yeah.
Also, I think a good little recap of everything, like just a written recap of everything we've done up to this point would be cool.
What do you mean, like what we just did today?
Yeah, just like a little checklist of like everything we've done up to.
A checklist. Okay.
Yeah.
I think the best thing, I'm gonna share the screen for a minute now.
Cool.
Hang on a second. Okay, I'm going to share the screen and I'm going to our module. Do you see the module? I mean, do you see the home page? Yeah. All right,
Yes,
go to the
we do.
module. Angel, rather than me writing it up again, I think the best way to do it is to look in each of these classes. I have that overview, right? So like for the components, here's the overview. It's basically a summary of what you need to know with components. And then we did resultants. Here's the summary of the resultants. I think it would be better if you want something written. I think that'd be more complete than if I try to jot everything down right now quickly. Oh, that's
Okay.
Friday. Don't
Yeah,
go to
for sure.
Fridays. Don't go to Fridays. Just go to Tuesdays and Thursdays. Overview of a setup. Then the next one would be an overview of 2 and 3D statics particles. The next one would be an overview of 2D problems using right-hand rule. Next one is an overview of 2D and 3D doing vectors. The next one is an overview of moment about a line. The next one is an overview of 3D problem moments with right-hand rule. I think the overview is better rather than if I just try to quickly write it down.
No, yeah, you're totally right.
Okay, let's look at this problem again. I have to move your pictures over. But remember, so the thing that Jason was saying is, if I'm trying to find the moment about X, Y, and Z here, in the end, I'm really finding out, everybody's with me, right? The problem here asks to find the moment about the X, Y, and Z axis. And really the X, Y, and Z axis all go through this point, right? So we're really finding the moment about point O. Hang on. We're really trying to find the moment about point O, but we want to know the value about the X, Y, and Z axis because we want to find the components of the moment about point O, right? So we looked at each of these forces, and what we did is we put our fingers in the direction of the force and we put our hand, our palm, towards the axis. And Jason was asking yesterday in office hours, well, aren't we trying to find the moment about O? Yes, you are, but you can't really face O because then you would be getting a three-dimensional moment. And what you want to do is for each one of these forces, you're finding out the moment about X, Y, and Z separately, because that's what gives us the perpendicular distance. So if we just look at this problem again, we're at Elizabeth. Elizabeth, tell me one force that creates no moment about one of the axes and tell me why.
Pass.
Okay. Eric, give me one force that creates no moment about one of the axes through zero, through the origin.
I'm looking at it. I might have to pass too.
Okay. Gerardo,
Yes, hello.
one force that creates a zero moment about one of the axes is X, Y, or Z.
B.
Okay, so force 150 pounds creates a zero about what?
About the z-axis,
How come?
because it's parallel.
Excellent. Next, Hyoji, give me another force that creates a zero about an axis. Okay, Isaac?
A creates no moment around the x-axis.
So, and let's say the force, right? A is a point, right? So the 300-pound force creates a zero
About the x-axis,
x-axis because
it's parallel.
Great. Jack, another one. Okay, Jason. What, Jack, you there?
Yeah, sorry, I just didn't hear what the last person said.
Okay. He said the 300 doesn't create a moment about the x because it's parallel. So give me another force that doesn't create a moment about an axis.
The 240 wouldn't create one around the Y
How come?
because it's parallel.
Great. Jason with an E, give me another force that doesn't create a moment about an axis.
Well, I think we did them all.
One more. For a
What?
different reason.
What? Okay, hold on. A different.
It's not because it's parallel.
You're like, turn it down. Let me think about this. I'm very curious.
Can I say it?
Yeah, well, someone, if it's on the tip
All
of
right,
your tongue.
Daniel C, go.
Let's
Isn't
see.
it? It's because it intersects.
Right. So which one?
Sorry, let me pull up the drawing first. For force of 150 pounds, it would intersect with the y-axis.
Okay, so Daniel, look at that closer.
Okay.
Put on your 3D glasses.
3D.
Here's the 150.
Fooled.
Here's the 150. It looks like it's intersecting Y, but is it?
No.
No, it's in front of it.
Oh yeah, so it's
Okay,
not
so
intersection with.
give me another one that's intersecting.
Oh, it's the 300-pound one.
Right.
That's intersecting with the
300
Y one.
intersecting Y, so it's 0. The 300 does not create a moment about the Y. Okay?
Good.
And remember that you're always, whatever point you're trying to find the moment about, make sure that you draw the axes through that point. Okay, you guys, I'm going to sign off now because I have a meeting with, I have a broad meeting with Karen, Carl, and Brandon. So I am going to save this. It's recorded. I'm going to save it and I'll post it to the lab class, today's lab class, okay? All right.
Okay.
So this weekend, everybody who has not met with me on an interview yet, make sure that you sign up today for a time. Sorry, those of you who have not met with me for an interview yet, make sure that you, by today, fill out that survey that says when you're available on Monday, Tuesdays, Wednesdays, Thursdays, or Fridays, whatever days I have. And then this weekend, I'll give you the schedule. Okay. All right. See you guys.
Thanks, Joanne.
Okay,
Thanks,
bye.
Joanne.
Bye.
Take care.
Thank you.
Yeah, you're welcome.